So for a lot of games, having a sort of targeting system to have a specific enemy or a specific object that you are focusing on can be really helpful. You can see here in my game that I've been testing, I have a targeting system that targets the enemy that is the closest to the center of your screen. And today we're going to go into two different targeting systems, one that does this based on screen space and one that does it based on world space. So just whichever enemy is closest to you in the world. And then when you have that enemy, you can do stuff like when I attack, it attacks towards that targeted enemy. And when I press like this magic spell, whatever, it does it toward that targeted enemy as well. So it's very useful, even if you're not making a action RPG, maybe more like an FPS, it can help with aim assist, all this kind of stuff. So here we are in an empty project. We're going to reconstruct both of these methods, and just as a little bonus, I'll throw in something where you combine both of those methods to weigh them so that things that are very close by you, even if they're not on the center of the screen, are going to take targeting priority as well. The full project, once it's been finished, at the end of this video, will be down below in the description for Patreon members and YouTube members. But let's get started. Before anything else, we need an enemy class. So I'm just going to make a character, I'm just call it enemy. And all the other enemies that I might want to add into this game would inherit from this, so that we can filter on this class fairly easily. I'm just going to, in the mesh here, put in a many. And of course you would want him to have an animation blueprint and all that kind of stuff. I don't really care too much for it, but we can just give him some animation blueprint, logic, and we have our enemy, at least a placeholder for the enemy. So let's place a couple of them in the level, just so that we have something to test this on. But now we can go into the third-person character blueprint and start working. So we're going to need a couple of things. First and foremost, I'm going to be adding a event tick. This doesn't necessarily need to run every single tick. So if you prefer, you could set timer by event, set the timer to something like 0.2 seconds, and then make a custom event here. This does make the targeting system a little less responsive because it's only running about 5 times per second, or about 10 times if you set it to like 0.1. So I like to do it in event tick just because it makes it a little bit more responsive. But on higher frame rates, this starts being a little bit overkill. Anyway, the first thing that we're going to do is we're going to sphere overlap. And this will create a sphere that will return an array of actors that it's overlapping with. So the sphere position will be our actor location. So get actor location. And the sphere radius, I guess we can promote it to a variable, or we can just set it to like 2500 or something like that. It might be nice to put this as a variable so that you can change it easily if you're going to reference this in multiple places. Then object types, we need to make an array out of. And in our case, we only want to really filter on pawns. If you also have something that is maybe world static or world dynamic or any of these other channels, you can add all the channels you want in here. For us, we're just going to do it with only pawns, because we're also going to set an actor filter class, and that'll be the enemy filter that we just made, the enemy class. So it's only going to return an array of actors that are enemies or child classes of enemy, and also have some collision that is marked as a pawn, which of course is the capsule component here that's marked as a pawn. Once that is done, we first and foremost get a return value on whether or not it found anything at all. If it didn't find anything, we don't need to do anything because there's no enemies nearby. If you have some kind of like dynamic system where it pops up your HUD for your combat when there's combat and it disappears when there's no combat again, you can do that here. If you have like a dynamic music system that changes the music when there is combat, you can do that here, all that kind of stuff. What we care about though is we're going to do two other functions, and we're going to be making those. So let's add a function which is closest enemy in world space, because that's the easiest to do. And that will take in an input of a enemy array. So we'll just make that enemies. I already have array type selected here, so we just need to set it to enemy. If you just get this as singular, you just click on it and you change single to array. That takes in our enemies. Now, we're going to for each loop over those enemies. And for each of those enemies, we're going to get the distance to it. So what we'll do is you actually want to hook this up the other way around. So the target will just be self, so the third person character. And then we want to get the distance to the other actor, which is the enemy from the array. And then we'll make a local variable down here. So not a normal variable, but a local one. And we'll call this distances. And we'll set that to being a float. And then we can come up here and set that as an array. So for every single enemy in this array, what we're going to do is we're also going to add its distance to an array like this. So now we have a corresponding enemy array that has the distances with it as well. Once this for each loop is completed, we are going to return some values. The first value that we're going to return is the entire distances array. So we'll call this enemy distances or something like that. So we can use that in some other stuff later down the line. And then also, quite importantly, is we will return the closest enemy. And this will just be a singular enemy type. In case the only thing that you care about is world space, this is the way that we're going to do this. We're going to make another function in a second, and then we'll combine the two together. But in case you only care about the world space, this is just all you need to do. And the way we get that is we find in our distances array, we find the minimum of the float array. So this is going to be the lowest value that this float array has. And that gives us an index. So we can get the same index from our enemies array. So we can get a copy, that index, and that will be the thing that we return. And we can be sure that this is going to work because we are adding the distances to this distances array in the same order that the enemies exist in the enemies array. So these two are always going to match. So that's the reason that we can do it this way, which is quite nice. Going back into the event graph, if this is true, we can do our closest world space, which takes in our enemies array, which actually needs to be an actor array, technically speaking. So we can just change that in here if you really want to, or you can cast everything, same difference. Let's just make this into an actor array. You might need to disconnect and then reconnect a couple of things because it's expecting an enemy reference and not a actor reference, but it'll do fine. So we can once again get a copy, and then this, it is closest enemy in this case. So for this, maybe what you want to do is you want to cast it to the enemy type. So that way, outside of this function, you just get an enemy out of it. But we can also change this output into just being a actor reference and then only cast it at the very end. That is usually better practice to do. Anyway, with all that, we can now put the out actors into this enemies array. And that will get us the distances to every single one of those enemies and the closest of those enemies. Next up, what we're going to do, we're going to make another function. And this will be the closest screen space enemy. Closest enemy screen space, whatever you want to call it. And this is going to take in the exact same thing. So this is going to take in an array of actors. So let's call this enemies and make it an array. But instead of just getting the distance to, we need to do a little bit more work for this. First thing we're going to do is we will get the viewport size. This is going to get us a vector2, and we can just promote that to a local variable. Call that something like viewport size. And the reason that we need to do this is because we want to get the center position of the viewport, for which we need to get the size of the viewport. Because if we divide this by 2, which we can do by right-clicking this and changing this to a float, so divide this by 2, now we get the coordinates of the middle position of the viewport. And we don't actually need the viewport size as a variable, so maybe we can just do viewport center as the variable. I change a couple of things around so that we set it like this. That makes a little bit more sense. Then we're going to for each loop over those enemies again. So for each entry in enemies, and then we'll add another function, and that will be project world to screen. And this will take in a player controller, which we can just get player controller. That's fine. It needs that because it needs to know which player screen to think about. Then the world position, which in this case will be the actor's world position. So get actor location. And then there's a bool for whether or not you want to do it like player viewport relative. That's only important if you're doing split screen stuff. So if you are doing split screen stuff, you want to enable this. If you're not doing split screen stuff, you really don't need to bother. That gets you the screen position. And here we can actually still do the same thing. So we don't need to do any difficult math or whatever. We can just get the viewport center, and then we can get the distance 2D between that and this actor's screen position. And we can make a local variable again here, which is the distances float array once again. And we can simply add that distance to there. And much like before, because we're iterating over this in the order of the enemies in this array, and that hasn't changed since the last time we did it, it's going to be adding them in the exact same order. So now we can add a return node once again, and here we can add a single output for the closest enemy, and then also add a distances array, which will be a float array. Doesn't need to be called distances array, just enemy distances or whatever. And we can do the exact same thing. So the distances can just be this array. We get the minimum float array. And then from the enemies, we get a copy of, and that is what we return as closest enemy. So now we have both functions in world space and in screen space that we can use, and we have arrays for both of them so that we can do some more calculation if we want to make like a weighted function to create something that will weigh things that are very close to you, maybe more heavily than things that are far away from you, but close to the center of your screen. So let's do closest enemy screen space as well. And for the most part, this is probably all you're going to need. But I do want to go over all the kind of little things you need to change and set up to make those two weighted things together into one distance array that you can pick from, because you're going to need to change a couple of things. Most importantly is these distances are just absolute distances. So if you have a radius of 5,000 that you're checking in, the first away enemies is going to have a distance of about 5,000. Same thing with screen space. If you literally just have more pixels, these numbers are going to be bigger. So in order for these two to be blended together and weight to each other, we're going to need to normalize them. We're going to need to get the distance in both cases on a 0 to 1 scale instead of an absolute scale. For the world space, that's actually remarkably easy, because if we just go back here to the sphere overlap and we promote this to a variable, our sphere radius, we can simply just divide this, right? So if we divide the distance here that we get to the other actor by our sphere radius, we just get a 0 to 1 percentage of how close it is to us. Meaning that if it is exactly at 2500, it's going to return 1. So that is the very furthest away that you can get. If it is exactly on top of you, the exact same position, this distance is going to be like 1, and it's going to be divided by 2500, so it's going to be 1/2500. So it's going to be a very tiny amount. So now we're going to be adding that instead. This will still function the exact same way, because they still get ordered, and we still get the minimum float value out of them, but now it's on a 0 to 1 scale. The screen space is a little bit more involved, so we're going to more or less construct that from scratch real quick. So what we still have is calculating the center of the viewport. We get every actor's location, project it to the screen, and then divide that by the viewport center. I accidentally removed that. But then instead of getting this as an absolute value, this is where we're going to need to do a little bit of math, which involves a little bit of trigonometry. I'm sorry to say, we'll go over this easily and quickly. And in order to normalize this, what we need to be able to divide this, so we can add a division node already, by the maximum amount of distance that we can have. But how do we calculate the maximum amount of distance that we can have? That is the difficult question. Because we're going to need to draw some triangles for that, right? The maximum amount of distance from the center of the screen is the 4 corners. That is the absolute furthest away that you can be from the center of the screen. But we don't have any values for that yet. So what we're going to need to do is we need to get the height, or the half height, and the half width. I'm doing this the wrong way around, but you get the point. We need to draw a triangle with the width and the height. And with that, we can then calculate the third side of that triangle. And that is the maximum amount of distance that our viewport can be, or that an enemy can be on our viewport away from the center. So what we do is we get our screen width divided by 2, which we already have as the viewport center, and then we split that structure up in. With that, we can use the power node, and we're going to put in an exponent of 2. So this is just squaring it. Like triangle stuff, a squared, b squared equals c squared. So we do this for this as well. Then we add them together, as you've learned in high school, hopefully. And then we get the long side of that triangle squared. So now we need to take the square root of it, which we actually just straight up have a square node. I didn't even know that. So I guess we can use that. We can use the square node for this, sure. And then we can take the square root of that, which will be the thing that we divide by. So another real quick overview is we get projected to world space, viewport center, distance, whatever. That goes into the top of the division node, and then the bottom of the division node will be the viewport center, split into X and Y. Separately, we square those, then we add those two together, and we get the square root of that, and that goes into the bottom of the division node. And now you will see, just because it's a little bit more complicated, I'm going to double check this, that we can print string this, and it will be a 0 to 1 value based on how close our things are to the distance away from the center of the screen. So the closer this guy is to the center of the screen, the closer this value is to 0. But as he goes off screen, his value goes to 1 and a little bit above. It's not like an exact science, especially with this aspect ratio. It's a little bit iffy. You can see it's a little bit more accurate at 16:9. But we also have this other issue where if we look entirely the other way, it goes up to like a value of 5. And if we walk away even more and then it gets stuck on a value of 1, and it kind of acts weirdly with trying to get the screen position of something that is not on screen, which kind of makes sense, doesn't it? So what we'll do is the answer from this division node, we will just simply clamp this. Scrolling up, we can clamp a float between 0 and 1 instead. And then don't forget to add them to the array. So now, even if these things are off screen, it will just tell you, hey, this is a value of 1. And generally, I think that you should do it this way anyway, to prevent any like weirdness or glitchiness with this whole like projection thing. So this is probably just like better to do it this way anyway. And now both of these are normalized to a 0 to 1 scale. So if you just want to linearly do this without any like curvature to the weights whatsoever, it's literally as easy as just making a new function, because of course, let's call this weighted closest enemy. And this is going to be taking in 3 things. And the first one of which is the world space distances. The second one will be the screen space distances, both of which are going to be float arrays. And then the third one will be the enemies, which of course is going to be an actor array. We're not even going to use the actor array at all, because we already have the distances for both of them anyway. So what we're going to do is we're going to just iterate over either the world space or the screen space distances, and do ignore my misspellings. And we'll simply just take any of those entries and add the corresponding from the other one. So we'll get a copy, that's actually quite relevant in this case, getting a copy, on the exact same index that we're on the for each loop right now. Add that to the value of our current array element, and we'll make a new weighted distance array, and that is going to be added to our weighted distance. And then we just do the exact same thing, right? We go through all of them, and on complete, we return. And this time, the only thing that we need to return will be the closest enemy. And we will just get a copy out of our weighted distances with the minimum value. That same index is what we will return. And now we're adding these two things together properly while they're normalized to a 0 to 1 scale. So if something is very close to you in world space, but on the edge of the screen for whatever reason, because it's walking up like from beneath you or something like that, you're still going to attack it instead of the thing that is maybe very far away, but at the center of the screen, and vice versa. Now, there's one last thing that we could do to give you even a little bit more control over how these things are weighted, and that is using curves. So let's make a new curve. I never know where they are, so I always just look for them. And this will be a curve float. You could make this as a composite curve table as well, if you wanted to, but we're not going to. Just going to do this as normal curves. So this will be the world space weights, and he will make a curve, add a key, It's a little bit of an annoying interface. I don't love this interface, but we're going to make a key at 0, 0. And you can middle click to make another key again. And this key will be at 1, 1. So this is just a linear curve that maps 0 to 0 and 1 to 1. So let's copy that over as a base. And this will be our screen space weights. So screen space weights. Going back into our third person character. In both of these functions now, the closest enemy in both world space and screen space, instead of directly adding this value to the array, what we can do is we can get this value and use it to sample that curve and instead add the result from that curve. So what we can do is, for ease, we'll just make two variables here real quick. This will be the world space curve. And this will be not of type float curve, which is somewhere in the struct here with one of these blue pins to it. What we want to get is the curve float object reference, because we're going to be referencing the objects that we made here, these assets. So we can just drag that in. Right now I'm in the world space function, and we from that can get a float value fairly easily. So we give in the in time, which is in this here, is the x-axis, and then we get the corresponding y-axis. So the value that we give in will be what we were just doing, our 0 to 1. And then instead we're going to be adding in the output from that curve into our array. And now we can say, okay, our world space, we actually want to weight that a certain way, right? So let's just change this to being cubic interpolation or whatever for both of these. Make these handles like unlock, so we can change them around a little bit easier. And now with this cubic interpolation and toggled weighted tangents, I can do whatever I want, right? So I can say 0 is when they're very close. 1 is when they're at the very edge of my detection. So if they're at the very end of my detection, very, very far away, I maybe want them to like get a value of 1, like very quickly, or nearing a value of 1 fairly quickly. I also only want there to be like a pretty small window here, up to like 0.2 or something like that, where they get given a disproportionately low value when they're close to me in world space. And everything in between will get graded kind of like interpolated properly. So kind of the same. And in screen space, we can do something similar, of course. So we select both of these, cubic interpolation, and unlock the tangents. And here I want to say, okay, only when they're really close to the center of the screen do I want them to get given a lot more. And when they're very far away, I want them to like be not that weighted. So we can make a kind of similar curve here. So like up to, this is about 0.3, I think. They get given a fairly low score, which is good, right? The lower the score, the better the chance of them getting picked. And then it very quickly shoots up into very unlikely to being picked. So they need to be fairly close to the center of the screen or fairly close to you in world space, one or the other, or both, in order to be the one that gets picked. And of course, we need to add another curve here into the screen space one. So screen space curve. From that, we get our float value, and that will be the one that we add to the array, and so on and so forth. And at the very end of all this, we now have our weighted closest enemy, and you can save that to a variable and do stuff with it. For now, I'm just going to be printing its display name. So let's print string, just the display name. And just for ease of testing this, what I'm going to do is I'm going to give this a text renderer, which will set up to a line in the center and just like exist kind of above their head. And then on begin play, we'll just set text for these to get display name for this object, so that it will display what they're called, so that we can actually like properly test this a little bit more. So if I just put a couple of these in the world real quick, we can start testing this. And pro tip, don't forget to actually give these curves their values. So I did forget that. So world space curve, screen space curve. And now we'll see, I can look at enemy 3 roughly, and that'll be the closest. And enemy 2 will be the closest to the center of the screen, because they're all about equal actual physical distance away from me. But as I walk toward enemy 2, and even if I look at enemy 3, which is now closer to the center of the screen, it's still going to be focusing on enemy 2, because it is closer to me, and the things that are closer to me have a higher weight to them. Personally, I would probably weigh the screen space linearly and then the world space with a pretty heavy curve. But as I move away from enemy 2, you can see it changes to enemy 3 fairly quickly, because when I'm not super close to him anymore, the screen space takes priority, and even to enemy 4 over there. But then when I go back closer to enemy 2, the physical space in the world becomes more important because it's a very, very low number. So that is the basis of a slightly more advanced targeting system that can weigh different things together. And maybe you even have your enemy have something like a danger value that you can then also add in there for its weight. So things that are more dangerous are more likely to then get targeted first, that kind of thing. You can make this as complex as you want and add as many different parameters to this calculation as you want. These are just the first two and the most basic two. Again, if you want this entire full project, which might have turned into 2 videos, looking ahead how long this recording is, I will see in editing. There's a link down below in the description to where you can download this entire project with the code that we have set up to play around with a little bit and try to figure things out if you're having any trouble. And a very big thank you to all of my Patreons. You can see them on screen right now. If you want to help out supporting the channel, there's a link down below in the description to the Patreon page. A huge thank you to my Cave Digger tier supporters, Sir J. Thomas,